So by applying this to a k-regular bipartite graph on 2n vertices, it's easy to prove that it doesn't have too many perfect matching. So let G be a k-regular bipartite graph on 2n vertices. Then its number of perfect matching is at most k factorial to the n over k. And also you can prove that in this Bregman theorem, if you analyze the proof carefully and then analyze all the cases when we get equality in this inequality, then you can actually show that this equality only holds for block diagonal matrix, in which each block has a square matrix with all entries 1. So you have like some square matrix. So these are like all 0 and these are all 1. So that's the only case you get the equality. By using that, again, you can show that this equality only holds for disjoint union of complete bipartite graph. Each of the complete bipartite graph is k sub kk. And this is only for bipartite graphs. And we can ask for, what's about non-bipartite graph? For non-bipartite graph, we can also define adjacency matrix. We already learned in the undergraduate graph theory that let A be a adjacency matrix of the graph G by defining in this way. AUB is 1 if UB is forms an H in G, and this is 0 if UB is not an H. Then by using Bregman theorem, we can also find an upper bound on the number of perfect matchings in general graph. Let's assume that 0 factorial to the 1 over 0 is 0. We do this because if there is an isolated vertex, then obviously there will be no perfect matching. Then we can prove this theorem. So let G be a graph with degree sequence d1 to dn, or degree list or degree sequence. Both are same thing. So we know that the degrees of the vertices in G is d1 to dn, but we don't know what graph is. But from that, we already have an upper bound on the number of perfect matchings, which is di factorial to the 1 over 2 di. And you multiply them. So proof is not so difficult using the Bregman theorem. So we have 2 here. So in order to get rid of these 2, you can just simply take the square. And when we take the squares on right hand side, and left hand side is also squared. So let's see what this term, perfect matching of G square, what kind of meaning does it have? Let's see that. So this is same as the number of ordered pair of perfect matchings in G. So, I mean, this single term counts all the perfect matching. So if you count the number of ordered pair of perfect matching M prime, then obviously you get perfect matching of G square. But once we have these two perfect matching, what we get is the union of two perfect matching. It gives a subgraph of G consisting of whose components are either even cycle or on edge. If you have say some perfect matching of a graph and another perfect matching, then we have this either edge if the edge belongs to both perfect matching, and some component which alternates the blue edge and red edge, which alternates the blue edge and red edge. So all of these are even cycle. So each component of the union must be either an edge or even cycle. So let curly H be the collection of such graphs which are subgraph of G, and it's a disjoint union of edges and even cycle. And let H be such a graph with, say, H1 component which is an edge and H2 components of even cycles. Then PMG squared actually counts H exactly 2 to the H2 times. What does it mean? So this specific graph here, this is H. This is counted if we take first matching this and second matching this. So for this M and M prime, we get this H by taking union. However, if you take again, let's say this and this and this, say M double prime, and the same edge, and this and this M triple prime, then again you get H. See what I just did? You take the same M and M prime, but in one component you shift it. these red edges belong to this M, but now in blue graph you take the other matching here, and which give you M double prime. So here there are two ways to divide this 6 edge into two matching, three edge matching and 3 edge matching. And here also two ways to divide edges into matchings. And you take one of two way, and then this has only one way, you just take it. Then that gives you one graph. And then once this is fixed, you have to choose the other way for the second one. So the second one can be determined from the first one, so that their union is H. So the number of ways to do that is 2 times 2. So there are 4 ordered pair of matching which gives the same H. So that's exactly 2 to the H 2 times. I mean 2 to the H too many different ordered pairs which give you H. So then what's the permanent? Permanent of A counts the permutation pi such that A U pi U is 1. For each permutation, we take edges U pi U with all vertices. What do we obtain? We obtain a spanning subgraph of G, which is disjoint union of cycles and edges. Give me a moment. Permanent of A So here the cycles could be all cycle. So it counts all the subgraph of H and possibly more. Moreover, each graph in this H, the disjoint union of edges and even cycle, is counted exactly 2 to the H2 times as any cycle of length at least 4 can be oriented in two ways. So what it means is that once pi is given, pi is say 1, 2, 3, 4, 5, 6, 2, 3, 4, 1, 3, 7, 8, 5, 6, 8, 7. Say this is the permutation. Then what's this edge? We have 1, 2, 3, 4. We have this. So this is not a directed edge, but u to pi u. Let's say pi 1 is 2. So let's direct in this way. And then 5, 6, 7, 8. And 9, 10. 9, 10 is on both ways. So this pi gives us this graph in, say, h. And this pi is not only one which gives you this specific graph h. If you oriented this in the other way, one of them the other way, then this is corresponding to pi, which sends 1, 2, 3, 4, 1 to 4, 2 to 1, 2, 3, while 5, 6, 7, 8 is sent in the same way. So this also corresponds to the same graph h. And how many pi's correspond to the same graph h is there are two ways to orient this, so 2 to the h, too many ways. And all of them are counted in this permanent. And maybe even more. So as square of this perfect matching of G counts all the graph in H, graph in this curly H. And each graph is counted exactly 2 to the 2H time. And permanence of A also all counts them. And maybe even more if there is odd cycle. And then by Bregman's theorem, we know that this is at most di factorial to the 1 over di. So now you take the square root. Then you get the desired inequality. So this gives you an upper bound on the number of edges. As I mentioned before, the equality could hold if we take a disjoint union of complete bipartite graph. KD, say D, KD prime, D prime, KD double prime, D double prime, then this equality may hold. And by, using the, I mentioned that this Bregman theorem give you an, equality if and only if the graph, the matrix you get is block diagonal matrix. Where is it? Yeah. Block diagonal matrix with the ones in here. And using that, you can actually show that you can actually prove that the equality in here also happens with the disjoint union of complete bipartite graph. So today we learned about this permanent, and which counts the number of matchings. But as I mentioned before, the permanent is a good tool to count the perfect matchings, but it's in general too difficult to compute. On the other hand, determinants are easy to compute, but it does not count the perfect matching. However, the determinant and permanents are only differs in the sign of its terms. So it's natural to ask whether we can somehow use these determinants to count the perfect matchings, because it actually counts the perfect matchings up to some signs. I mean, those terms, the number of terms in determinant formula is the number of perfect matching, but somehow they cancel each other. So that's the problem. So we want to somehow overcome that difficulty. So one of the possible ways, we change some 1 to say -1 in the matrix, in the adjacency matrix. And so that all the terms in the determinant calculation have the same sign. So instead of A, you change it into some other matrix, say A prime. In there, some of the ones become -1. And then you compute a determinant. In this determinant, its formula is that you take a product of AI, pi I, and you take the all I, and then you multiply by the sign of your pi. And here you want to make sure that each of these terms somehow miraculously having all the same sign. Then the result is you take the absolute value, then result is the perfect match, number of perfect matching of G. So can we do this? And another approach is that consider the determinant of the matrix as a function, not a number. As each AI, say pi I, being variable, so that they cannot cancel each other. And then use that somehow to get some information about perfect matchings in graph. We may not be able to count the perfect matchings, but can this tell us something about the graph? So next time we will take the first approach and then see how it will turn out, whether it gives us some useful fact. So that's what we will do next time. Thank you for listening.